Hello, my name is Jacob Gersh. I am a second-year PhD student in Virginia Tech studying with Dr. Christina DiMarino at the Center for Power Electronic Systems, which we call CPES. And today I'll be talking about prototyping and evaluation of a 10 kilovolt silicon carbide MOSFET power module and how we evaluate the reliability of some of the components critical to that module's function. So as we all know, we're here at the Wide Bandgap Summer Workshop through Power America. Wide bandgap devices have a tremendous ability to impact a number of different markets within power electronics, different technologies spanning from grid-scale power electronics implementation and renewable energy integration. But to harness all the benefits that wide bandgap devices have over conventional silicon power devices, we needed more advanced packaging technology that can operate at the higher voltages, the higher speeds, and the higher power densities that might potentially be offered by wide bandgap devices. So you can see here an image of dimension drawing of the module designed by CPES, boasting of the 18 watts per millimeter squared power density and a low parasitic inductance of 4 nanohenry. And all of that is made possible by the geometry and the technology incorporated into the package. The 10 kV module designed through CPES implements a stacked direct bonded aluminum DBA substrate design that allows us to harness all of the enhanced benefits of our 10 kilovolt wide bandgap silicon carbide devices. That includes increasing the PDIV, the partial discharge inception voltage, by 50%, reducing the common mode current in the module by tenfold, and resulting in a low power loop inductance of about 4 nanohenry. You can see that the substrates are stacked both on the top of the module and the bottom of the module to implement this geometry to harness all of those benefits and improve the performance of our power module overall. In order to fully harness all of the benefits of stacked substrates, we need to ensure that the reliability of those substrate stacks are equivalent or greater than the rest of the reliability of the rest of the components in our package. There's little research currently done on the reliability, particularly the thermomechanical reliability of stacked substrates, and the research that currently exists does not examine the large area silver sintering that we use to bond our substrates at CPES, which I'll discuss in a later slide. As you can see from the existing research, this stacked aluminum DBC, direct bonded copper substrate, has cracking in the ceramic and delamination of the metal traces from the ceramic substrate, as well as some failures in the bond between the two ceramic substrates in the stack earlier than 150 cycles, thermal cycling between minus 55 and 195 degrees centigrade. In order to maximize the reliability of the substrate stacks that we're investigating, first we need to optimize the process that's being used to actually bond the substrates together. We use a large area silver sintering process that is fairly low pressure, 1 to 3 megapascals during the actual sintering step, and uses a sintering temperature of about 250 degrees centigrade. As you can see from the diagrams below, when we're working with a nanosilver preform, it's first deposited on the substrate using a process step at 1 megapascal and then sintered for 60 to 90 seconds using a pressure range to determine where the optimal pressure is for silver sintering of between 1 megapascal and 3 megapascals. And this process is being compared to a very similar process using a screen-printed nanosilver paste. So the two processes are compared and samples are placed in a thermal cycling chamber in parallel to monitor their bond degradation and the propagation of any cracks or defects in the bonds by cycling them from minus 55 degrees centigrade to 200 degrees centigrade. And this cycling is taking place at the National Renewable Energy Lab in Golden, Colorado. So CSAM images are taken of the entire group of samples, some made with this screen-printed paste, and some made with this silver preform, both of them using a pressure range of between 1 and 3 megapascals to determine which provides the optimal method for creating samples that are the most reliable. We're very excited to see the results of this investigation later in the summer as we continue to monitor these samples throughout their thermal cycling and reliability lifetime, so that can inform the reliability design of our module going forward and determine the optimal way to stack these substrates so that they can survive the predicted lifetime of the module. So just reiterating with my name and contact information, please feel free to reach out if you have any questions or comments. Thank you so much for listening.